Hey everyone, welcome back to the channel. I am Agnes. I usually make videos about data science, productivity, self learning, etc. And today we are doing a deep dive into a concept called bias mitigation in data science. We will not only talk about the concept behind bias mitigation, but I will walk you through a Python notebook that I've created on this topic for my portfolio. The dataset that we are using is the adult income dataset. So I will, you'll understand why I chose that particular dataset when we go through the code. So let's get started. So first, a quick refresher: machine learning. So machine learning models learn from data. If the data is biased, the model will learn that pattern, and it is an ethical issue as well as a technical problem. In conclusion, a biased model is a broken model which we cannot use in real world uh, applications. I will show you how bias sneaks into datasets, how to measure bias, uh, and we will be discussing two major methods: model-centric and data-centric approaches. So this is a commonly used dataset to explain bias because this dataset has columns like race, sex, and there are subgroups in both those columns. So you can already see the issue. So I am downloading the dataset from UCI machine learning repository. If you're working on Google Colab, you have a lot of options. You can download and upload the data to your drive. This particular data file really uh, doesn't really have the column names, so we have to learn any. So we have to explicitly mention the column names: age, working class. Then there's a column that shows this is an unnecessary column. You don't need this column. This column is stands for final weight. It's a statistical sample weight used by the US Census Bureau. I have to say a disclaimer: this dataset is from I think 1984, and some of the terms used in this dataset are not considered okay anymore. So the first thing, I'm gonna load the dataset. We use I'm gonna use Panda read CSV, but this is the data, so we can see this age, this education, marital status, occupation, relationship, whether they have a family or not, race, sex, capital gains, capital loss, hours per work, native country, income. So it's essentially a classification problem because the label column is income. Um, so in order to follow this tutorial, you need a basic machine learning knowledge. If you're watching this particular video, I am assuming you know a little bit of data science and basic concepts. So we are entering into the EDA. I'm just gonna check. Here I'm just checking the shape of the dataset, and we have around 30,000 rows and 15 columns. So like I said, this column is unnecessary, so I'm just going to drop it. Then we have to check for missing values or null values. Since this is a academically used dataset, this dataset doesn't have any null values, which is very unlikely to happen in real world. You will definitely get null values and you will have to manage them using your domain knowledge and data science knowledge and your based on the task you are doing. But even though we do not have missing columns, this dataset has placeholders for missing values. So they have used question mark in multiple bases for in place of missing values. So we cannot include any special characters. We are so essentially for number model, all the data has to be transformed into a numerical format. So that's what we are going to do here. You can see the special characters here. So in word class we have 1000, almost 2000 question marks. In occupation we have almost the same number of question marks, and in the native country column we have around 600 question marks. So I'm just gonna replace it with a string unspecified, and later we will be using one-hot encoding to convert the whole thing into a numerical dataset. So I'm just going to use dot replace to replace this particular string. So after replacing, I'm just checking here to see if the question mark still exists. You have to verify your pre-processing steps. Sometimes it may not work when you're setting up a long pipeline. Now data training process is almost done. Let's get into visualizing the distribution. If you look at the distribution of the sensitive columns, race and sex, as we identified before, and see that there's a there's an imbalance in the number of different subgroups. We can literally see from this visualization that the subgroups are indeed not balanced. So we are going to see how we can mitigate this problem. As an initial step, we have to encode the categorical columns. So these are categorical columns. We have a lot of 1, 2, 3, 4, 5, 6, 7, 8 columns. We're converting the target variable income into a numerical value. Sometimes there will be extra white spaces in column names. We can just use the string.strip function to just remove that before doing your whatever function that you're applying. So display the value counts for your converted income to verify. So we have converted the income column into values of zeros and ones into 0 and 1. It's the label column, so we have to separately handle it before applying onto hot encoding. So in our feature engineering process, we are making deliberate choice to keep sex male and sex female columns. If you know how on-code encoding works, so it will create a separate column for all the separate categories in your categorical variable. For example, in the categorical feature sex, there will be 2 columns which are sex male and sex female. But in order to avoid multicollinearity, we usually, one hot encoding usually do not keep, one column, just creates the sex male column, and if the sex male is 1, then the sex female is definitely 0. So the algorithm knows that. That's how the algorithm is set up. Usually, we don't have to specifically, keep the multicollinearity. So we have to remove job first equal to true parameter or just set it false. So yeah, that's what they did here. Then moving forward, splitting the data 80% testing, 80% for training and 20% for testing. So after splitting data, I am going to train the model using a baseline model. So the baseline model is a simple, straightforward model that serves as a benchmark model for our further experiments. So it's not supposed to give you the best accuracy, but it's a starting point for us to compare our more complex models. So I tried to train a simple logistic regression from a scalar, but I could not, it was not converging. And the reason could be that if the data is not standardized, it takes a lot of time to converge. So I am just, if different features are on different scales, the data usually takes a lot of time to converge. So in order to solve that problem, you can just scale the data using standard scalar. If you do not know on routine coding, like scaling normalization, you have to, go and learn the math behind it, because maybe I'll link a fundamental math course, because there's a lot of math in Michelin that you have to understand. Otherwise, you wouldn't be able to come up with solutions when you're doing a problem. Mostly metrics, multiplication, and I scale the data. Now I'm retraining the baseline model, and it was super fast. It worked pretty well, and the accuracy I got is around 86%, which is good. I'm not gonna lie, but precision is around 75 for the greater than 50K income class or the positive class, and recall is around 61%. Looks really good for a logistic regression model. We will see. We are going to break it down into subgroups. We already identified the sensitive features. Those are sex and race. We have to segment the data into the subgroups and evaluate metrics. So I am this is my script to get the all the metrics from each subgroup. And if you look at the subgroup, you can see the recall for female people in the dataset is much lower than the recall for males. And if you look at gender, it's also evident that for different genders, the algorithm has learned different. So we got different recall. So there is a bias. This is an unfair prediction. So the scalar double bias, and across the different regional groups, we are seeing more bias. So I'm just going to plot the output that we got from the baseline model. Yeah, it's obvious from the visualization. The blue bars are accuracy, the orange bars are precision, and the green bars are recall. Yeah, I'm just explaining the research here in my notebook. The notebook is available on my GitHub repo. I will link the GitHub repo in my description so you can just take a look at it. Maybe clone the repo and test the code, clone the repo and use it to learn. So we are going to try a data-centric approach to mitigate bias, and I am just going to upsample the subgroups. So if you look at the data, and if you look at the distribution of the label column income, then over the target feature, there is a yeah, there is an imbalance. So I'm just going to fix that first. But it did not solve the imbalance between subgroups because, well, it did not really focus on the subgroups. So we need a vector targeted oversampling. This is something that we usually do in academic projects. We just use oversamplers to just create more examples in the minority class, but it doesn't work if you need a biased model because each subgroup has to be biased. So after this step, I went and oversampled all the minority classes, and I apparently the subgroup examples to somewhat of a good amount, and it did not work because the whole data-centric upsampling, rebalancing the data did work. There are other methods as well. You can try them out. So I will link my uh, blog post about mitigating my bias in machine learning down in the down in the description. It describes the theoretical methods and tools you can use. In this example, I'm just using one method for upsampling and one method for data-centric approach and one method for uh, model-centric approach. So in our case, the data-centric approach did not work. Recall shot up. If you look at the subgroup, some of the minority subgroups, you can see that the recall is like 1 or close to 1, which you will think is a good thing, but the precision is going down so much. So the key lesson from this experiment that I learned is fixing the data alone doesn't really guarantee a fair model. Sometimes it just creates new problems. Yeah. So I always note down the reasoning behind my steps in my notebooks because number one, I might forget it later. Also, if I'm sharing it with somebody, it will be easy for them to sense of the code. Why did our balanced logistic regression model failed? Um, so when the recall is extremely high and the precision is extremely low, this is what happens. So recall measures the model's ability to find all the relevant cases within P dataset. In our project, it measures how well the model correctly identifies individuals who truly belong to high income class. A high recall score means the model is good at finding almost all the actual high income individuals. the higher recall came at the cost of extremely low precision. So, precision measures how many of the positive predictions made by the model were actually correct. So, this is a classic trade off. By trying to achieve perfect recall for a minority group, our oversampling strategy made the model so lenient that it started making many incorrect positive predictions. Uh, so this is often worse than law recall because it leads to a high rate of false positives, which can have significant negative consequences depending on the real world application. So, what's the key takeaway? Our attempt to create a fair dataset resulted in a model that overcorrected, leading to a high rate of increased predictions for minority groups. This proves blindly applying data balancing techniques to the data doesn't always work, or it could have detrimental effects. That's the real complexity of creating fair models. Now we are going to try a model-centric approach. I mean, there are multiple model-centric approaches. I do explain them in my blog post in brief that. So while we are transitioning to a model-centric approach, here I'm just going to use the library called Fairlearn. So TensorFlow has a few other libraries. Um, so TFDV is really good for evaluating and understanding the distribution of data and stuff. TFNMA is good for, and there's TFMA, there's MINDEF. MINDEF is a very common method. So you can try anything. So Fairlawn's mitigation algorithm works by defining a sensitive feature and a performance metric to equalize. So yeah, we are going with a Fairlawn is a powerful library for this task. It directly intervene with the model and corrects its predictions when the model is training. So we don't have to do anything with the data. So I'm just going to apply. I mean, you can just go to the Fairlearn documentation and learn how to pick the model written just as Gemini. And yeah, you have to wrap. Yeah, you have to just fitted the model, and this is the output. It did perform a little bit more better, more balanced output. So if you look at this approach that I did with using Fairlearn is called threshold calibration. This model-centric approach adjusted the prediction threshold for each subgroup after the model was trained. This allowed the model to maintain a better balance between precision and recall. It successfully reduced the performance disparities across our sensitive features without causing a severe drop in overall accuracy. So, yeah, it's a complicated problem. Uh, you have to have an understanding of your business objectives. You have to have an understanding of your domain. That's why data scientists this weird career where you have to know a lot of different subjects: math, stats, computer science, um, organizational psychology, maybe a little bit of business. So finally, I'm just using the AS statistical test to check if the improvement in the prediction is statistically significant, and our p-value is essentially zero. That means the improvement in our metrics is statistically significant. So what did I learn from this project? Uh, Number one, oral accuracy is misleading. You always need to check subgroup performances. There is a lot more things you can do from a feature engineering perspective in ML data science careers. In ML and data science, usually 5% of the workflow is modeling. The rest is a lot of infrastructure building, pipelines, feature engineering, training data, stuff like that. So that takes a lot of time, and there are a lot of things to do in terms of feature engineering. And lesson number 2, data balancing can work sometimes, but it can also backfire. Lesson number 3, model-centric approaches. Model-centric approaches could help. Model-centric approaches like threshold calibration could give practical results. So what's the takeaway? What's the one thing you so in a nutshell, uh mediating in a nutshell mediating mediating bias is a in a nutshell mediating bias is an iterative problem. There's no one step fix. There's no one there's no immediate fix, but every step that we take towards building fair AI systems is a win. So if you want to check out the full code, I have my GitHub link in the description. There are, if you just search, there are big projects which got abandoned by MNCs before because of this problem, because the real data has a lot of unclear biases, and they will reflect if you are not using responsible AI practices, the model will not be reliable. Real world data will always be unfair, and it's the responsibility of the people who build AI systems to make it robust and trustworthy. Yeah, so always learn about responsible AI practices and the tools you have. In the current market, there's a lot of research in this area, very necessarily because AI and the growth in AI is going on a extremely high pace. Don't forget to like this video if you find this useful, and subscribe for more data science content. Thanks for watching.